is joint with Marc Lackenby. So I turn that up. So this talk concerns the geometry, hyperbolic geometry in particular, of alternating knot complements. So throughout the talk, we're going to be dealing with alternating knots. So let me draw a picture of what an alternating knot looks like. I can actually draw two knots. This is the 5-2 knot. Is it? Wait, 1, 2, 3, 4, 5. Yeah, 5-2 knot. Okay. An alternating knot is often represented by a diagram. So it's just a 4-valent graph in the plane. Each vertex has over-under crossing information. And for an alternating knot, if you start somewhere and start walking around the knot, then you will alternate between going over, under, over, under, over, under, over, and so on. Right? So it's alternating knots. Now, alternating knots are some of the most studied knots. This is because in the knot tables with small numbers of crossings, alternating knots are very common. So these were studied heavily by people like Tate. But what we're going to be doing today is hyperbolic geometry on alternating knots. And so I'll say something about this in a minute. Many knot complements admit a hyperbolic structure, but somehow alternating knots seem to best encode, the hyperbolic geometry seems to be very well encoded by the diagram. And that is all a little bit sketchy for good reason. A lot of what we have seen, observed for alternating knots comes from experimental evidence. We've seen it for lots of examples. There are several open conjectures about hyperbolic geometry of alternating knots. And today we're going to be talking about one of those conjectures. Okay, so to give a little bit of background, in the early 1980s, Thurston was doing a lot of work on hyperbolic manifolds, and he showed that many knots are hyperbolic. Okay, and that can be made more explicit, but I won't for now. Alternating knots were some of the first examples, alternating knot complements, I should say, not complements. So the manifold is S3 minus K. These were some of the first examples of 3 manifolds with a hyperbolic structure. So for example, Riley was looking at the complement of the figure 8 knot in the 70s. Thurston realized that that was a figure 8 knot complement, late 70s, early 80s. And then when Jeffrey Weeks built the program SnapP, then a lot of low crossing knots were examples of hyperbolic manifolds which were studied using this computer program. So this finds, computes structure or hyperbolic structure on a 3 manifold. And many of the examples they were looking at were low crossing knots, which are often alternating. So alternating knots were big examples of things that were studied. Okay, and so as we, continuing then with some history. So in 1984, Manasco was able to show that all alternating knots, except the 2Q torus knot, or 2Q torus knots, put an S there, for odd Q. These are all hyperbolic.
Do you want to say prime?
Yes, I do. Okay, so we're going to take prime alternating knots. That is, we don't want to deal with connect sums of knots in this knot. Okay, so and the 2Q torus knot, what that looks like is you have 2 strands and Q crossings, and then those connect up like so. Okay, so this is your 2Q torus knot. We're going to be looking at pictures that are similar to this through a lot of this talk, where you have 2 strands that run in and twist around each other and form some number of bigons in the diagram. So you can see these are all bigon regions in this diagram graph, right? This is called a twist region of the diagram. And so what Monasco's theorem says, if you have at least 2 twist regions, then your knot is going to be hyperbolic. And we're going to see that twist regions are they encode a lot of the hyperbolic geometry of a knot, of an alternating knot. Okay. So if you add to this Mostow-Purcell rigidity, so I guess this was the 60s, but this tells you that the hyperbolic structure is unique of 2 isometry. And then Gordon-Lukey showed that knots are determined by their complement. And so all of this together means that hyperbolic geometry is a complete knot invariant. So hyperbolic geometry seems like it should be the way to study knots starting back in the 1980s. The issue, though, is that it is often difficult to relate. This is going back to Nathan's talk. It's difficult to relate the combinatorics of a diagram, this topological material, to a geometric structure on that. And so this is the same type of problem that Nathan was talking about. You called it quantified Mostow rigidity?
I think it's called quantitative.
Quantitative Mostow rigidity. So given a diagram, let's relate that to the hyperbolic geometry. What are hyperbolic properties? Okay, and so following Steve Kirchhoff, I actually call this type of problem WYSIWYG topology. What you see is what you get. Okay, so that is properties that are prominent topologically really ought to be somehow show up geometrically as well. There ought to be some relations. Okay. In order to tell you exactly a little bit more about the problem that I'm going to talk about today, I need a few definitions. But I should say too, a lot of what this problem is motivated by a lot of examples. In particular, using SnapP to compute hyperbolic structures on knots, and then examining the results of what is done. So I brought an example that I computed, and I'm going to show you what this should look like. But again, I need a few more terms in order to explain the main results. Okay, so for those of you who are less familiar with this, we're going to say a cusp of a finite volume hyperbolic free manifold is an end of the manifold which is homeomorphic to a torus across an interval and isometric to a Bohr-Wall neighborhood. Okay, so I should explain a little bit more what this means. So let's jump into hyperbolic 3 space. And throughout the talk, I'm going to be looking at the upper half space model. Okay, Okay, so x, y, z, so that z is greater than 0. And so this is a picture of that. We've got our plane at infinity, and then we have a point at infinity, and hyperbolic space is in the middle. And a horoball about infinity, I'll denote this, h infinity. This is the set of points z greater than some constant. So I'll be talking about open horoballs. And now my manifold is hyperbolic, which means that its universal cover is hyperbolic 3 space. And I can quotient out by a group, a discrete group of isometries of hyperbolic space. This is the fundamental group. Acting by deck transformations on the universal cover, right? So standard topology here. And so for every element, gamma, inside of my group, my bigger group gamma, is provided that gamma does not fix infinity, then when I take this group element and I apply it to h of infinity, it's going to take the point at infinity to some point on the plane, and it's going to take the horoball at infinity to some ball which is tangent to the plane. Okay? So one way of looking at hyperbolic structure on a manifold would be to fix some sort of a cusp, fix a horoball neighborhood in the universal cover, and then take all of your elements of the fundamental group and draw the pictures of what you get when you translate those, when you apply those. So you'll get, provided you start out with a large enough C, so you're high enough, these are all going to be disjoint, but there are countably many of these things corresponding to countably many group elements. Okay? Okay, so if we start high, these are all distinct. We can start expanding the horoball about infinity. So decrease C. And for a little while, this will still be embedded. But eventually, you'll reach a point where this horoball about infinity becomes tangent to one of its translates under the fundamental group. Okay? And at this point, we say that the cusp that arises from this is a maximal cusp. So we're going to need that. So a maximal cusp is a maximal embedded horoball neighborhood. Okay, so then a little bit more topology geometry. The fundamental group is going to have a subgroup which fixes the point at infinity. So I'm going to denote that by gamma infinity. And in the case that we are looking at a knot complement, then you can think of this group as being generated by a meridian and a longitude. Right? Generated by meridian and a longitude, mu lambda. And if you take your cusp at infinity, so just take h infinity, and you quotient out by gamma infinity, then this is the cusp, right? This is homeomorphic to T2 cross 1 infinity. And this torus is going to inherit a Euclidean structure from the hyperbolic metric on your 3 manifold. So another definition, we say that the cusp shape of the manifold is this Euclidean similarity structure. Okay? And so then finally, the cusp volume, this is the volume of h infinity, sorry, quotiented out by gamma infinity, where h infinity is the maximal cusp. Okay, yes?
Are you dealing only with knots so that you'll only have to deal with one cusp?
Yes, so in the case of links, there will be multiple cusps. We're just talking about knots because we're just, yeah, we just want to deal with the geometry of one cusp, yes.
So the different cusps in a link that have different shapes and different volumes and all kinds of.
That's right. The cusp shape is, this is usually typically just the similarity structure. So this is going to be well defined, but the volumes will vary depending on your choice. There will be a choice of the maximal Horoball in that case, or Horo cusp. But in the case of knots, it's well defined. It's unique. Any other questions? All right, so snap P, one thing that it can do is it can take a diagram of a knot, so for what Weeks built, and it will cut it into pieces, and then it will basically find a hyperbolic structure, numerically find a hyperbolic structure on those pieces, and give you a triangulation of your manifold that encodes the hyperbolic geometry. But when you have this hyperbolic geometry, you want to take a look at it, you want to see what the geometry looks like, and then if you go and use some of the graphical tools, one of the major tools is the Cusp neighborhood viewer. And basically what that did is it would take a cusp and apply, find you the largest Horospheres corresponding to that. So I have an example here of an alternating knot. Let's see. So this is a screenshot of a knot that I drew on my computer. It's not the highest quality, but hopefully you'll be able to see it okay. This alternating knot, I think this is the 817 knot over here. And I typed it into snap P. I had it confused. This is snap pi, actually, I should say. So this is Nathan Dunfield and Color and Dunfield's new version of this that will work on my Windows 7 machine, but not my Windows 8 machine.
Please report such things, because I was not aware. Mark tried it on Windows 8 and it worked, so.
I probably need to talk to you later. I didn't have enough time last night.
Consider it reported. Details, I need details.
All right, so in any case, I plug this in, and then I asked to view the cusp neighborhood, and this is what I got. And so what are you looking at? Your head is at infinity, and you are looking down at this. These are the Horoballs that correspond to group elements of your fundamental group. This purple rectangle here is a fundamental domain in hyperbolic 3 space for the Euclidean torus. Okay, so that encodes the cusp shape. So now the question is, how does this picture of all these balls relate to that diagram over there? So by Mostow rigidity, it should, but it's not necessarily obvious how that worked. And so, well, let me say this. So, Morwen Thistlethwaite, I saw an example of, or he went through an example of this. I saw this about 10 years ago, some slides for a talk that he gave somewhere else. And what he did, I'm going to do this for you too. He started on the knot. So I'm just going to start at a point here. We'll start there. And he started walking around, and my arrows are going one. I'm going to walk opposite my arrows. But then I'm going to label the crossing. So this crossing here is going to be 1. And then we have 2, and then we go through 3, 4, 5. Right, so where am I going? 6, 7, back to 1. We write the sequence 1, 2, 3. Well, okay, hold on. Let me hold off on writing the sequence. We go back to 1, and then we come around, and we hit 4 and 5 again, and then we hit the 8th crossing there, and then 2, 3, 6, and back to 1. Okay, so I'll write that down in a second. This is the complement, after you quotient out by the fundamental group, this is going to give you the complement of the knot. So the hyperbolic structure here. So everything that we see in the complement of this diagram, we should be seeing in this picture here. Okay. So in particular, there are these arcs that run from top of a crossing to the bottom of the crossing. So I'm going to call that a crossing arc. Crossing arc. Okay. And when we are running along the cusp, that is, when we're walking along this four-wall neighborhood, we ought to see the tops and the bottoms of these crossing arcs as we step our way through. So let me go through this again. Okay, so if we start at this big black dot here, and we walk along the knot, then we're going to see the bottom of crossing arc number 1 first. And then as we continue, we're going to see the top of crossing arc number 2. And then you would think we'd see the bottom of crossing arc number 3, except notice these are actually homotopic. There's a homotopy right there, right? They slide through the bygone right there. So now I'm going to write the sequence. So we go to 1, and then we go to 2, which is homotopic to 3, so we should see that. And then as we continue, we'll hit a crossing arc corresponding to 4, which is homotopic to that of 5. So 1, 2, 5, and then we hit 6, and then we hit 7, and then we're back to 1 again. And then we hit 4, and then we go to 8, and then we go to 7, and then 2, 3, and then 6, and then 1. Okay, so this is our sequence of the crossing arcs that we need.
Is there a reason to pick 4 for one representative and 5 for the other?
No, I meant to pick 4 for both of them.
Sorry.
I think it was the second A.
Did I made a mistake? Okay, so let's check.
6, 8, what?
The second 8. Oh, I missed it. Right, where should I go? Okay, so 1, 2,
Second to last.
Right. I think it's
6, 8.
6, 8, 1. Thank you. Okay, did I get it? That's going to be important because my example won't work if I have it wrong. All right, so we want to see these crossing arcs in the diagram. And this is something that Warren Thistlethwaite noted in these talk slides that I saw back in 2002. If you just start, well, you have to pick your starting point somewhat carefully, and I did. But then you start labeling the larger horoballs. So I'm going to call this guy 1 here, and then this guy 2, and then 4 is this one. These are the same, right, by meridian translation. And then we hit 6, and then 7, and then we go back to 1 again. So notice that this horosphere here is the same size as this horosphere here. Okay? Now, if these do indeed, the way that I'm labeling these, I'm trying to indicate that the arc that's going from infinity down to this seems to be related to the crossing arc that I drew into this picture over there. And if they were the same thing, if that is correct, then this horoball should be the same size as this horoball because there would be an isometry between them.
No, size is just some artifact of our Euclidean eyeballs, isn't it?
No.
All horoballs are the same.
No, because the horoball at infinity has a particular height. But then remember, every single group element is an element of PSL2C. That's going to take your horoball to something. There will be one that will be full size. There at least one that's going to be tangent. But all the others are not allowed to get, once you've expanded to that point of tangency, then all the others are a fixed size. So they could be smaller. Right? So they're going to be all different sizes.
Another way to say it is that the size is related to the length of the arc relative to those horoballs.
All horoballs are the same, but some are further away than others.
Further away from what?
The one at infinity.
Eyeball.
From the one at infinity. From the horizontal one and
And things that are far away are smaller.
Yeah, so does that make sense? So there's some distance. Maybe let me draw a picture side view. There's going to be some horoball, because this is maximal cusp, there's going to be somebody who's tangent. And that is big. This guy, there's going to be some distance in here, and you're going to see that distance. Your eyeball will see it because this ball will be smaller. There will also be really teeny tiny guys, most of which aren't drawn. And that corresponds to a very long arc here. in the
I guess
hyperbolic
my
geometry.
only point was, you've got this whole family of parabols, tangent to infinity at a certain point. And then there are these hyperbolic isometries called homothenys,
Right.
which move back one right onto the other.
So that
in
maps
some
this
sense,
onto
they're all
this.
the same.
The infinity parabol to be at some fixed height length.
Yeah, you'll see a tangency, a point of tangency, but that's typically not going to be at infinity anymore when you apply this isometry too. So, in any case. Okay, so well, continuing on, so hopefully that kind of answers your question. But continuing on with our sequence, the next thing we hit is 4. And then notice again that we have same size torvalls here and here. Okay, and then we hit 6. Where's 6? Oh, I'm sorry. I was thinking that's the wrong size. Okay, 8. 8 is a new one. And then 7. Okay, so 7 versus 7. And then 2. So notice that these are the same size as well. And then 6. And 8 again. Okay, and 1. All right, so you can eyeball that for a minute. And this isn't a proof that anything is happening. This is just a picture of what seems to be happening by magic. So by looking at a lot of these pictures, this led Thistlethwaite to make a conjecture. So he conjectured that for any alternating knot, these crossing arcs, which are the arcs which run from the top of the crossing to the bottom, the conjecture is that these are short. Okay, so what does that mean? These are infinite arcs, right? They run from infinity to infinity when measured outside the maximal cusp. Okay, and I don't think he wrote this in a paper somewhere. So just in slides of talks that I've seen, the most sharp version of this conjecture that I have seen was that the length is bounded by log 8. Okay, so I'm going to call this the strong conjecture, strong Thistlethwaite conjecture.
So Jessica,
Yeah.
is it also suspected that these crossing arcs are isotopic to the geodesic?
Yes, it's suspected that they're isotopic to this particular geodesic, right? Yeah. Okay, so let's see.
And another question?
Yeah.
So, does this conjecture imply you can recover the DT code from?
I'm not sure. I don't know what the DT code. I'm not that familiar with it.
It's the
Well, the
sequence of
Delta-
numbers, basically.
Oh, it is the sequence of numbers. Yeah. So I believe that it does imply.
Bygons.
By,
So bygones are a little tricky.
Oh, I see. So the DT code picks up bygones as well. Okay. So never mind. Yeah, you have to get rid of these bygones. You'll have edges that are homotopic to each other.
So is there also, this is saying there's an upper bound on length, but there should also be a lower bound on length if the twist region has size 1.
There should be a lower bound on length. Well, I mean, the length can be 0.
Right, so but I mean, so is the, maybe you're going to say this, so is the length sort of somehow proportional to the size of the twist region?
I don't know if that's been conjectured or not. I don't know. I don't know what that looks like.
Can you tell
That
me?
would be interesting. I don't know. I haven't looked at that much in the example.
but
Yeah.
another question, but aren't bygones detected from the looking at 2 4s?
Are the bygones detected by looking at these?
There was a
fours?
3 and a
Yeah, so the 3 is, the
But-
4 and the 5 got collapsed, the 2 and the 3 got collapsed.
so look at this picture.
And from this picture, I don't know of any obvious way to see knots.
Because they're much shorter, right? The 2 is bigger.
But so it's not a
Anything
The
good,
2 and the 4 are bigger, yeah. So I don't know, I mean, maybe.
but the 8 is almost as big, right? It's not, the 8's a single.
So Snap P is tons of fun. Oh, I just pushed that out. Oh, well, whatever. Okay. So that conjecture over there is the strongest version that I've seen. A weaker conjecture that's similar, but that doesn't lend itself quite so much to the nice pictures, is the following. So rather than say something specifically about alternating knots, if this stronger conjecture is true, then it will be true that the cusp volume of an alternating knot is bounded below by a linear function of the twist number. Okay, so I defined for you what a twist region was. I need to define the twist number. Yes?
Can you turn your screen 0 off?
Oh, do you still want to, I'm done with my example. Do you still want to see it for a minute? Sure. When I get back to this board, I'm taking it away. Okay, so the twist number. Remember, a twist region is a string of bygones. Or, I guess I should say as well, a single crossing which is adjacent to no bygones is also a twist region. So this diagram here, the crossing number was 8, but it's only got 6 twist regions because the bygones 4 and 5 bound to bygone, 2 and 3 bound to bygone. Okay? So example, so I did need your that example, right? 6 twist regions. And then we are going to define, let me push this up. The twist number to be the minimal number of twist regions in an appropriately reduced diagram. Okay, and I won't need it for purposes of this talk, so I'm just going to brush the reducedness under the rug. But the diagrams that I'll be showing you for examples are all going to be reduced. Well, okay, maybe I should say something. If you have crossings like so on either side of a box, you can perform a flight to put those two together. So that's the reduction that you do. Okay, and nugatory crossings eliminate that sort of thing, as usual. By work of Dasbach and Lin, this twist number, notation, I'm going to denote the twist number by twist of k. Dasbach and Lin proved that the twist of k is an invariant for alternating knots.
Doesn't it also follow by the Flepping conjecture? Flepping theorem?
I'm sorry?
Doesn't it also follow by the Flepping theorem of monastic?
Does it also follow by the Leibniz theorem? Probably, it might.
By the definition.
Is that?
By definition.
Yes, by this reduced
Yeah,
property, yeah.
If you reduce one of the flaps.
Okay, so today, we do not have a proof of the strong conjecture, but we're going to prove this weaker conjecture that the cusp volume of this thing does behave as expected. It's bounded in terms of the twist number of these knots. Okay. Yeah?
Is it true that the cusp volume is sum of the logarithms of algebraic numbers just like the usual volume, or is it?
Is the cusp volume the sum of the dilogarithm? No, I don't believe so. So to find the cusp, well, to find the usual volume, the way that you're talking about, I think you find ideal tetrahedra and you find the volumes of those and add them together. The cusp volume is just looking at the tops of the tetrahedra. So typically what you do is you cut off a plane and then you integrate above that.
So it's frequently algebraic, for instance.
It's an algebraic number.
Often. Well, for the figure 8, it's something like 2 root 3.
Isn't it half the area of the
It's very graceful.
Yeah.
Okay,
Yeah.
thank you.
Okay, yes.
The cusp field is a subfield of the cusp.
Yeah, twist numbers. This is algebraic.
Yes. So, well, in this case, for alternating knots, yes, I will come back to that question. So, Marc Lackenby found an estimate on the volume of alternating knots. He found linear bounds above and below in terms of the twist number. And so, from that, you can easily get the upper bound, or the cusp volume is also bounded above by the twist number because it's bounded above by the volume. But the fact now that there is a lower bound on the volume of the cusp volume in terms of twist number means that the cusp density of these knots are uniformly bounded below, which is somewhat surprising. So maybe let me just say that while I'm talking about it. So cusp density. This is the volume of a maximal cusp divided by the volume of the manifold. Okay, and this there's a well-known upper bound. Do you see? Okay, now I'm going out of order on my notes here.
Sorry, I think there's just a little crossing change in that diagram. They should both be the same here.
If you're going to get something interesting, I can. This isn't allowed either.
That's not. Yeah, but that's not even a minimal diagram.
Yeah. Yeah.
Okay.
Yes. Yeah. That didn't help, but but it's the same. It's the same sort of thing. Yes.
Okay.
Okay. So I am looking for how you spell. Here we go. Borowski? I don't know how to pronounce that either. Borowski. So in 1978, he proved that there's an upper bound on cusp density. And the number he got was square root of 3 over 2 V3. V3 is the volume of a regular ideal tetrahedron. But there is no lower bound. In particular, even for knots in S3, there is no lower bound. So Luque and Mario Udave-Munoz found examples of knots whose cusp density is approaching 0. So Luque and okay, but so by work of Lackenby, as I mentioned before, there exists, and I should say this has been improved by various people. I'll say that in a second. There exist constants. I didn't write these down. Such that the actual volume of an alternating knot, alternating, is bounded by linear functions of the twist region. Okay, and this was improved. So these are explicit constants by upper bound by Agel and Dillon Thurston, and the lower by Agel, Storm, and Thurston. Okay, so we know that the volume itself is bounded, but on the other hand, the cusp volume is bounded. And so a corollary of our work is that the cusp density of alternating knots is uniformly bounded below. Okay, so somehow alternating knots carry a lot of their volumes in their cusp. And that would be one good reason that the diagram of an alternating knot seems to have so many more geometric, or seems to be so much more related using SnapHeat to the geometry of this thing than many other examples of knots.
Can I ask a historical question?
You can ask it.
The conjecture that you're proving, was it conjectured before Marc Lackenby's theorem on volume? Because it sort of makes plenty of sense in light of that theorem, but was it a previous insight?
Yes, I believe so, although I'm not exactly sure when, because I heard about it before this was published, I believe. But as I said, only from some talk slides. So, yeah, other questions?
I guess, may I ask one more? So
Okay.
it's reasonable to conjecture such a thing for links. Just there exists an embedded cusp whose density is not too small for an alternating link. Would your methods prove that?
It may be reasonable to conjecture that for links, yeah. They might. They might prove it. We haven't thought about it though. Okay. Okay, so let me write down the theorem at the very least. Where are we? And then I'd like to give an idea of how the proof goes in the time that we have, which is less time than I anticipated, but that's okay. Okay, there exist constants. I call all my constants C something. These are different constants. C1, C2, C3, such that if K is a hyperbolic alternating knot with maximal cusp H, then some constant times the twist number is less than or equal to the volume of the maximal cusp is less than or equal to some function here of twist region, linear function. And moreover, all of the constants in this theorem can be made explicit. Okay, so this is good news for me. I started my career doing cone deformations, and you need explicit constants to be able to work with these. So this means that we can use the numerical values for these and plug them into other geometric tools and obtain geometric information, for example, on Dane fillings of these. That's the good news. The not so good news is that our constants are not completely optimized yet. And currently, our C1 is about 3 times 10 to the negative 13. Okay, so that's not the worst constant that you will see in your geometric topology career. You attend enough talks, but.
It's not the worst constant you'll see this week.
That's right. We'll see.
Is there a conjecture about which knots are going to achieve the two bounds?
Well, my conjecture is the lower bound is pretty bad. This 10 to the negative 13. That's
So
too low.
is this one of these deals where there's going to be some sequence of knots approaching that?
If there's a sequence of knots approaching a lower bound, I don't think so. I don't think that there's anything along those lines. The figure 8 knot achieves the upper bound, and no other knot. But the lower bound, I don't think anybody has thought about that at all.
Well, is there something that would say the total number of crossings in one of your knots pushes this volume down toward that lower bound?
No, I don't think so. No. Yeah, I don't think crossing number really plays any role at all.
Except as far as it contributes to twist number.
That's right. That's right. Yeah.
Crossings per twist region should push you toward either the lower bound or the upper bound.
So
Sure.
Dave is conjecturing the crossings per twist region should push you one way or the other. So.
I am, yes. Based on experimental evidence for a different family. But
Okay.
so it might be a foolish conjecture.
So I suppose, I should give a little bit of related work. I've been thinking about Cusp volumes for a little while. So in work from 2006, I think is when 2007 it was published. So Cusp shapes, or Cusp volumes, I should say, of highly twisted knots have this behavior. So what is a highly twisted knot? This is where every single twist region has at least 134 crossings in it, I think was the number that I came up with for this result.
What is this behavior?
This behavior, this linear bound, right? The Cusp volume is bounded above and below by, right, by something. Something here plus something here. Okay, and then Peter Coauthors and I proved it for two bridge knots. Okay, and then of course there has been a lot of computer evidence along the way giving evidence for this conjecture. Okay, so let's give a sketch of the proof. There are some ideas that go into this.
Does this give you any idea about the Cusp shape?
Does this give you any idea about the cusp shape? Kind of. Okay, so remember the cusp shape is the shape of the torus, right? So we know by the sixth theorem, so Marc-Lackenby, that the meridian has length of less than 6, or less than or equal to. And actually that was improved by Adam, so I should put his name down. For alternating knots, he knows that the meridian length is less than or equal to 3. And so then you have this bound on the meridian length, and you have a bound on the cusp volume, then that will tell you that a longitude has to be related to twist region, or no, twist number as well, right? Longitude is roughly twist region. That's as precise as you can get, though, in terms of the actual shape of the torus from this. Okay, so what we're going to do is we are are going to find short arcs in S3 minus K. And we're going to find about twisted K of these, okay? Now this is a great idea. It hasn't worked for about 30 years though, so we need to do more than just go looking for them. So the way that we're going to find these arcs is we are actually going to be considering, so instead of finding the short arcs in S3 minus K, first we're going to find the arcs in essential surfaces, which can be immersed into S3 minus K. Okay, so if I've got about twist of K arcs in a surface that is essential, and then I map those into my 3-manifold, because the surface is essential, those arcs will remain essential. There may be an issue though. Distinct arcs here may actually be homotopic in the larger 3-manifold. And so step 3 is we're going to control over counting. Okay, so that is if there are 2 homotopic arcs here, sorry, 2 distinct arcs here, homotopic here, we need to eliminate that. Okay, and then once we have this, that's basically the proof of the theorem.
So when you say short is like a
Bounded.
like universal independent of K or something.
That's right.
Okay.
Bounded universally. That's right. That's right. Okay, so let's see. Okay, so the theorem that we are going to use to get these bounded length arcs, I'm going to call the surfaces theorem. So this is to us. So let F be a finite area hyperbolic surface. And we're going to take H of F and embedded horizontal neighborhood of the cusp of S, or of F. Then there exists at least area of H of F over 8 pi disjoint embedded geodesic arcs with length at most 2d, which is some number in terms of the area of the surface and the area of the cusp. Okay, so basically what this theorem is saying is we're going to find a surface, and provided we can show that the surface has a cusp with area roughly the twist number of the knot, then we're going to pick up a lot of arcs which are bounded by this number. Again, we want to make this a constant, so we're going to find a surface whose area and whose cusp shape is bounded by twist number, basically. Okay. So okay, so there are really two cases to consider. So the first case is, suppose that you have a bounded number of crossings in each twist region. So at most, say n crossings per twist region. Okay? In this case, there is a very nice surface that we can use. We're going to take the disjoint union of the checkerboard surfaces, which I'll call blue and red. So checkerboard, disjoint union of checkerboard surfaces. Okay. So the reason why so I'm drawing a little piece of my alternating diagram. These lines, this is supposed to indicate a tube around my knot. Okay. So the checkerboard surface, the two checkerboard surfaces intersect at crossing arcs. So we'll have one there, one there, one there, say. One of them is going to come up. Let's see, it's going to go around this way and down this region. And then it's going to twist through the knot, like so, and then come around and meet the bottom of this arc there. And the other checkerboard surface, blue, is going to run around this way and meet that arc on the other side. And then it's going to come through and be on this side, right? So it's going to come up and around like so and come into that crossing there. So here's the blue checkerboard surface. The red is on this side and this side. And the key point here is that for every crossing arc, the union of the red and the blue run over two meridians. So red, union blue, run over two meridians per crossing. And it's well known that a meridian has length at least 1. And so we get a cusp in this of these surfaces has area roughly 2 times, or has area at least 2 times the crossing number. Okay, so area of the cusp of F is greater than or equal to 2 times the crossing number, which is at least 2 times the twist number. Okay. On the other hand, we can find the area of these surfaces easily as well. So the Euler characteristic is let's see, is that right? So the Euler characteristic is the crossing number minus 2. Basically, the union of the two surfaces fills out the projection plane. It's going to have a hole for every crossing. So it's a crossing punctured sphere is the Euler characteristic of that. Okay. Okay, so with these 2 pieces of information, we immediately pick up a large number of disjoint embedded geodesic arcs with bounded length. And so this is going to give us a cusp estimate, provided we can control overcounting. So for the overcounting, then suppose we have 2 arcs, gamma 1 and gamma 2, that are homotopic. So this is supposed to represent a disk that realizes that homotopy. So if they are homotopic in the 3-manifold, they've got their endpoints on the knot, on K. Okay? You can do a little bit of work. So you consider D intersected with your surface. And a little bit of work implies that it's going to intersect, say, the blue surface in vertical parallel lines like this. Which basically means that if you take D and you cut along the blue surface, then you get what are called essential product disks. Which have been well studied. And so Lackenby in particular looked at essential product disks inside of alternating knots, and he showed that any essential product disk will always run over some collection of bigons in a twist region.
Are
like
these
so.
singular essential product disks for you? Because it's a homotopy?
No, you can, with work,
Okay.
you can turn it into an embedding. So these are non-singular. Okay, but okay, so now we use the fact that this condition here, we were assuming there are at most n crossings per twist region, and so there's a bound on the number of these things that can be homotopic. And then, so putting all of this together, dividing out by overcounting, you get the result. So that's the sketch of the proof in this first case. Okay? And it looks like I am out of time, but basically in the second case, what you're going to do, now you may have twist regions that have a high number of crossings. You're going to take your checkerboard surface and you're going to twist it up. So if you take a knot that looks like, or a link now that looks like this, so alternating link with a couple of crossings, and then encircle it, or throw in this crossing circle is what it's called. This is going to meet the blue checkerboard surface in 2 meridians. If you twist, so this is going to be homeomorphic to a manifold with a high number of crossings. And your meridian under this twisting goes to a 1 over n curve. So this is going to spin around some number of times. To get your knot, you Dane fill. And that means you're going to put in a solid torus here. For each cross section of your solid torus, your meridional cross section, you're going to be meeting this surface an even number of times. Attach an annulus, or 2 Mobius bands, just by connecting opposite edges that all run through the core. Okay. And this is going to give you an immersed, possibly ugly surface, but it's going to have some of the same characteristics that the checkerboard surface did over there, and you can use that to control overcounting. Okay, so I will stop there. Thank you.
Questions?
Yeah.
So, can you say the thing about the 2 meridians per crossing thing? I didn't understand that in the picture.
Yeah. So let me try and draw it again. It's the best way I know to explain that. So these things, the way that you build a checkerboard surface is first you take a disk and you fill in the regions. So there's going to be one over here, and then the red is going to have another one on this side, right? And it's going to meet up here, and it's going to be a twisted disk, and then it's going to go around the back, like so, and connect like so, and then up and around that way, right? So this is going to trace out a curve that starts at the bottom, wraps once around the meridian, and connects over here. The blue, though, is wrapping the other way. So it goes this way, wraps once around a full meridian, and connects over there. And where do they meet? Well, where they meet, you get exactly this red and this blue here trace out a full meridian. This blue and this red here trace out a full meridian. So you get 2 meridians.
Oh, I see. So the point is that those curves you draw, and they're somehow, they're not geodesics, but their length is bounded by the length of the
That's right.
meridian. So,
That's right.
so you
That's
know
right.
that it has kind of a long.
That's right. I should say too, because these are essential surfaces, we're going to pleat them.
So like ideal triangles bent
Yes,
on.
that's right. So we straighten an ideal triangulation, we pull back and we get a hyperbolic structure on the surface, and then we do hyperbolic geometry. This hyperbolic geometry over there, without even thinking about our manifold, and then we come back. Yeah. Yeah. Question? Yeah.
Same board all the way at the top. Just leave it where it is.
Oh, okay.
At most n crossings per twist region. Can't you just take any alternating knot and look at all the twist regions?
Yes.
Take the maximal one and call that n? I don't
Yes.
understand why that's even.
So the problem is right here for the overcounting. So we're going to get some number of arcs, right? It's going to be about the twist number. But it could happen, they may be homotopic in like so. And in the very worst case, if you take a single, if you run around a single diagon, then you have top and bottom are both homotopic to crossing arcs. There are n homotopic crossing arcs in here that are all going to look distinct in your surface. And so your estimate is going to have an n in the denominator. And we want a uniform bound independent of the knots. So this one, you would say, all right, I have a diagram. I know that the highest number of crossings in the twist region is 75. That means I get a bound of this over 75. But I want something uniform over all knots. So yeah, thanks for letting me clarify that a little bit more. To get the uniform bound, we've got to get rid of this n. And that's why we do the twisted surface instead. That'll take care of that. That'll remove that. Questions? It's interesting.